Hello everyone, welcome back to IMSE881 Linear Programming. Today we're going to talk about some numerical example for primal affine algorithms and also dual affine algorithm. Let's look at the primal affine algorithm first. And this is a document on Canvas as lecture 10 numerical example document. Has some of the steps I developed for illustrate a numerical example and also give you some insight on how to get an initial feasible solution to start with the algorithm, and some of the, also including some of the implementation consideration in this document as well. So let's begin as example 7.1 primal affine algorithm numerical example. And we have this linear programming problem. Minimize -2 times x1 plus x2 and subject to x1 minus x2 plus x3 equals to 15 and x2 plus x4 equals to 15 as well. x1, x2, x3, and x4 are non-negative. So this is apparently x3 and x4 are slack variable for less than equal to constraint. So here is the constraint matrix A, right hand side B matrix vector, and the cost coefficient vector C. I'm going to follow exactly this document for the theoretical document we have previously in this subject, and follow at the very end I have a summarized algorithm to present the primal affine algorithm. So let's review this really quick one more time. Initialization k equal to 0, k naught is greater than 0, and a times x naught equals to b, and we can compute a due solution omega k and sk. Then we can calculate the direction for y. Y is affine transferred x, in a sense, a negative xk, capital Xk times sk, and check for the optimality. And the optimality right here represents if the magnitude of the y actually is less than certain tolerance, and both x and s are positive or equal to 0. Okay. Then we can calculate the step length equals to a small a number slightly smaller than 1, could be 0.99 and 0.95 divided by negative dyk of I, which is negative. Then we update my primal solution, k equal to k plus 1, and continue doing so. So this is what we have. Let's look at the numerical example. This example, I have A, B, and C already given. And I'm going to follow exactly the algorithm we talked about in that document, a theoretical document. First, we're going to define x naught, capital X naught. Is the diagonal is the current solution of x naught equal to 10, 2, 7, 13. Okay, and I'm going to pre-calculate a thing called a times x naught squared. So this is a times, and then I'm going to calculate a times x naught squared times a transpose, just this times a transpose. Then take inverse of that. So the reason I'm doing so is exactly the way I'm doing in the Excel spreadsheet. I'm going to demonstrate a little bit. Okay, so here what I have is, after I calculate a times x naught squared times a transpose inverse, I can calculate the omega naught. Okay, and after I calculate omega, the due solution, then I can calculate the due slack equal to C minus A transpose times omega naught. So we can calculate due solution correspondingly, and then we can test the current duality gap is 2.1187. Next step, we're going to calculate the dy naught. Dy equals to negative x naught times s naught. Okay, and we notice that in this dy, there's two negative portion. Okay, it's on the one which is negative 9.3475, another one is negative 0.1003. So I'm going to choose the step size alpha. Assuming a step size alpha is 0.99 and divided by those two, who is less than or equal to 0. So the minimum one of those will be this one, 0.1, which is this guy. Okay, it's the smallest one. 0.1061 is my step size, alpha naught. And I can update my x solution, primal solution, x1 equal to x naught plus alpha naught times x naught times dy, because I need to scale back, affine transform back to the dx. So this is a new solution for x, okay? And the new objective function has been improved from negative 18 to begin with to negative 32, almost negative 32. Doing next step, okay, the current solution, x1, put it into diagonal time and calculate a times x1 squared and calculate a times x1 squared times a transpose inverse. This is what it is, okay? And then I can calculate omega 1, which is due solution, current due solution. So you see I pre-calculate the x, a times x, okay? A times x to begin with, and then I'm multiply by a transpose and take inverse. And this portion of taking inverse is one of the significant computational burden here. So I can calculate the current due solution, then I can calculate corresponding due slack solution. And I notice that there are two, actually, negative right now. And I can calculate the dy as well. Okay. So negative means they are not feasible. However, the duality gap is equal to primal solution times due slack, that's equal to negative 1.827. And calculate the direction of y. Okay, I have two negative components as well. I can calculate the corresponding step size, which is this guy as well. Okay. So what I can do is I can calculate x2. I'm sorry. Here is x2. Okay. I have some calculation mistakes on the alpha 1. Alpha 1 equals to 0.3407. Then I can update my x value correspondingly. And I use this MATLAB for all the matrix computations, so I don't have to be so concerned about the calculation mistake. And the objective function after update at new x improved from negative 32 almost to 44.79. Can do one more step. Now x2, capital X2 equals the diagonal of x2 and a times x2 squared, and then inverse of a times x2 squared times a transpose. Then we can calculate omega 2 is the due solution and the due slack. So you can see that the due solution converges to negative 2 and negative 1 almost. And the due slack converging to 0, 0, 2, and 1 in that case. We can calculate, and duality gap now is converging to 0.2103, continues shrinking, and the direction for y equals to negative x1 times s2, and therefore, actually s2 is here, right here, times s2 equal to 0.0007, 0.0011. They almost converge to 0 in the first two components, and negative 0.0835 and negative 0.1286. So I can calculate the step size one more time for alpha 2, update the primal solution. And here, with this new primal solution, the objective function value improved from negative 44.7879 to negative 44.9689. So, so we can see that actually the primal solution converging close to 30 for the x1, 15 for the x2, 0 for the x3, and 0 for the x4. So, and the optimal value is actually negative 45. You can continue to verify that. And following this document, we talk about some of the implementation issue, how to get the initial feasible solution for our problem, okay? Either using big M method or using tube-phase method. And I'm not going to go over this, and this is for your reading, because once we're adding more variables in here, either using two-phase or big M, adding artificial variable, and we will increase the dimension of the problem, how we can not increasing the dimension of our matrix variable, and we can pre-calculate them so they don't have to be using a huge matrix as described here in this document. So now we're ready to see how this particular algorithm works by using a Microsoft Excel. All right, let's back to our Excel spreadsheet. This Excel spreadsheet, I follow exactly the algorithm and example, the algorithm we illustrated previously, and let's explain this using a slightly different example. Okay, minimize negative x1, x3 minus x4 equal to 0. That means x3 equals to x4, and x1 plus x2 plus x3 plus x4 equal to 1. And that's my problem. We can easily verify this problem is the solution actually convert to x1 equals to 1 and rest of them equal to 0 in that case. So this is fairly simple. A matrix is the yellow area, blue area is the B vector, C vector is the gray area. And I can calculate initial, we can choose an initial primal solution, initial due solution, initial due slack solution, and the duality gap equals to negative 0.01. Actually, this is the to begin with. Okay, so then I can go ahead and calculate the capital X, diagonal equals to X, A times X squared, inverse A times X squared times A transpose. Okay, right here. After that, I can follow the exact solution to calculate the due solution, omega and S. Okay. That's what we have right here, omega and S. And I can calculate the corresponding dy, okay, dy based on the negative xk times sk in that sense. And I find inverse, I find transfer back, that's the dx, this is direction for x's. Okay, double check a times dx equal to 0, the magnitude of dy. Here we're assuming alpha equals to 0.99, and I can calculate the step for each one of the alpha, 0.99 divided by dy, right here. Okay, so choosing the minimum one without consider this negative one. So after I determine the beta, which is the step size, and I can update x, I can update omega and s was calculated over here already, so I just copy it over. So this is my new duality gap. All right, one more step. X, capital X, a times x squared, a times x squared, a times a transpose inverse. Calculate the new due solution, Calculate dy, again, dy equal to negative capital X times s, which is this guy. And inverse affine transfer back to dx and verify a times dx equal to 0, the magnitude of dy. Calculate the step size again, choosing the proper step size 101. Update my primal solution, then you can see that only x1 is close to 1 right now, and rest of them is getting closer and closer to 0. And I can update my due solution, which is copied from here, the current due slack solution, copy it from here, and that's it. One more step. X, capital X, a times capital X squared, a times capital X squared times a transpose inverse. Calculate new due solution and due slack. Calculate the dy equal to negative xk times sk. All right. And after that, I can calculate the step size. Actually follow the step number 5. All right. So I'm calculating the possible step size for each coordinate of dy and choosing the minima positive 1 and ignore the negative 1 and use that as my most conservative step size or maximum step size. Using this step size to update the primal solution, due solution and due slack, just copied it from here. And this is very easy to implement in the sense. But you can see that and the duality gap still converging smaller and smaller. And eventually, I let it run for 6 iteration. Okay, at the 7th iteration, actually it converges to 0, converge to the optimal solution. So the primal solution be 1, 0, 0, 0, due solution be 0, 1, and due slack will be 0, 1, 1, 1 in that case. And the duality gap converge to 9, actually 10 to the 10 to the negative 9. And also you can see that the magnitude of dy converges almost to 0 as well. So these are the very easy steps to follow. I just laid it out as closer to as the numerical example. I showed it in the lecture notes 10 numerical example, but I'm using a different problem. And you're welcome to convert this spreadsheet to the problem example I have in the document. I just want to show different problems so you can see how they converge differently in each problem. You're welcome to update. So what I did is basically I manually construct the first step, like here. Okay, like here, using the step, calculate x, capital X, to calculate a times x squared, times calculate a times x squared, times x a transpose inverse, update do variable, update do slack, calculate dy, inverse transform back to dx, double check a times dx equal to 0, calculate the magnitude of dy, direction for y. Then I can calculate maxima possible, the step, and using that populated here so I can update my X solution right here. So this Excel spreadsheet is on Canvas. You're welcome to download and double check. You can play with different problem settings, see if it converge and everything. All right. And that's therefore Primal solution. I intended to continue using the next video to show the do affine scaling algorithm. We'll come back to that. See you in the next lecture video.